Singular value decomposition. First, the decomposition of A involves an m by n diagonal matrix of the form sigma is equal to D 0 0 0. See, what we are doing is we are given with a matrix A for which we have to find singular value decomposition. So first we have to express A in terms of U D V transpose. This is called the singular value decomposition of A. What is U, what is D, what is V transpose, we will see one by one. So here A can be of any order. A can be of order m by n, and the matrix D, diagonal matrix, should also be of the order m by n, then only this is possible. U is normalized model matrix of A into A transpose. What is normalized model matrix of? First, step 1, you have to find A into A transpose. Then for this matrix find the eigenvalues, then find the eigenvector. After finding the eigenvalues and eigenvectors, you have to write the model matrix of A into A transpose. Let T be the model matrix of A into A transpose. Then the eigenvector corresponding to the largest eigenvalue should be written first. That is U3, U2, U1. For example, 1, 2, 3 are eigenvalues. Then the eigenvector corresponding to 3 should be written in first column, 2 should be written in second column, 1 should be written in third column. Then divide this matrix, then divide the matrix with norm of each vector. Thus obtained matrix is called model matrix of A into A transpose. Similarly, find the normalized model matrix of A transpose into A. After finding U and V, we have to find D. For D, what we have to do? Before finding D, we have to know an important property, that is non-zero eigenvalues of A into A transpose and A transpose into A are always same. This property is very important. For example, A into A transpose eigenvalues are 1, 2, 3. Then A transpose into A eigenvalues are also 1, 2, 3. Non-zero eigenvalues of A into A transpose and A transpose into A are same. For example, A into A transpose eigenvalues are 0, 1, 2. Then A transpose into A eigenvalues are compulsory 1, 2. But 0 is an eigenvalue of A transpose into A. We cannot say directly without seeing the matrix. So non-zero eigenvalues of A into A transpose and A transpose into A are always same. This important property we have to remember before finding or calculating the diagonal matrix D. So we will see why this is happening. See, we know that determinant of AB is equal to determinant of BA. So determinant of A transpose into A and A into A transpose are always same. And we also know that trace of AB is equal to trace of BA, because principal diagonal elements never change. So trace of A transpose into A and trace of A into A transpose are always same. So for example, our matrix is a 3 by 3 matrix. Then what is the characteristic equation? It is lambda cube minus trace of A into lambda square plus sum of minus of leading diagonal elements into lambda minus determinant of A equal to 0. Here trace of A for A into A transpose and A transpose into A are same, and determinant of A into A transpose and A transpose into A are same. So this eigenvalue only depends upon leading diagonal coefficient, that is coefficient of lambda. That will be also same. How we will see it in this proof? See, we say that lambda is an eigenvalue of A only if Ax is equal to lambda x for some x where x is an eigenvector. So by applying this definition of eigenvalue, we will find out this one. See, let lambda be a non-zero eigenvalue of A transpose into A. There exists x not equal to 0 such that, see, our matrix is A transpose into A. So let us suppose this is equal to B. So Bx is equal to lambda x, we can say. What is B? A transpose into A into x is equal to lambda x. So multiply both sides by A. If you multiply both sides by A, then you will get A into A transpose into A into x is equal to A lambda x. So you can write this as A into A transpose into Ax is equal to lambda times x. Since lambda is a constant, you can pull it out from the matrix multiplication of matrices. So what we are left with, A into A transpose we got, that is required matrix, and Ax, let us say this Ax is y is equal to lambda times y. See, this is of the form Ax is equal to lambda x. If Ax is equal to lambda x, then lambda is eigenvalue of A. If A into A transpose into y is equal to lambda y, then lambda is eigenvalue of A into A transpose. Initially we considered A transpose into A. Finally we got A into A transpose. Initially we considered lambda as an eigenvalue for A transpose into A. Finally we got lambda as an eigenvalue of A into A transpose. This says that non-zero eigenvalues of A into A transpose and A transpose into A are always same. So this property is very important. If you want to refer the proof, you can refer from this one. So non-zero eigenvalues of A into A transpose and A transpose into A are always same. So no need of calculating the eigenvalues separately for A transpose into A, if we are already getting all the non-zeros eigenvalues of A into A transpose. We will see in this problem. See. So how to calculate D once we will see. And what is D also. D is diagonal matrix. What is D? D is a diagonal matrix with its elements written as root of eigenvalue in decreasing order. What does it mean? For example, eigenvalues of A into A transpose. For example, eigenvalues of A into A transpose are 1, 2, 3. So eigenvalues of A transpose into A are also 1, 2, 3, because from this property non-zero eigenvalues will be same. So suppose A is a matrix of order 2 by 3. A is a matrix of order 2 by 3. If A is an order 2 by 3, then right. Okay. We will see in this problem so that you will getting more clarity how to take these eigenvalues. 1 minute. So let's solve this question. We can understand easily what is saying. Find the singular value decomposition of this matrix. Okay. Now we have to find the singular value decomposition of this matrix. So first step. What is step 1? What is singular value decomposition? A is equal to U D V transpose, right? First we have to calculate U. Calculating U. What is U? U is normalized model matrix. Normalized model matrix of A into A transpose. Normalized model matrix of A into A transpose. That we have to calculate. For that we have to calculate A into A transpose. Okay, first we will calculate A into A transpose. See here. A into A transpose is equal to 1 1 0 0 1 1. This is A. 1 1 0 0 1 1 into A transpose is 1 0 1 1 and 0 1. 1 0 0 1 1 and 0 1. Okay. Multiply these two. This is a 2 by 3 matrix. This is a 3 by 2 matrix. Resultant will be 2 by 2 matrix. So 1 2 we will get. Next 0 1. So 1 we will get. 0 1 1 we will get. 0 1 plus 1 2 we will get. So this is A into A transpose. For this A into A transpose, find out eigenvalues, because A into A transpose rangane we have to find the eigenvalues, right? So characteristic equation lambda square minus trace of A into lambda plus determinant of A equal to 0. Lambda square minus trace of A is 4 lambda plus determinant of A is 3 is equal to 0. Since coefficient sum is 0, 1 is a root we can say, and 3 is a root we can say. Remember this property. Remember this important note. If A plus B plus C is 0 in ax square plus bx plus c, then 1 comma c by a are its roots. 1 comma c by r its roots. So I directly wrote those roots. We can also calculate by using other relevant formulas. So lambda equal to 1 comma 3 we got. We have to find the eigenvector corresponding to lambda equal to 1 and 3. Okay. Case 1. Lambda equal to 3. First we have to take the largest eigenvalue. So lambda equal to 3 we have to calculate. So A you know how to calculate the eigenvalues already. A minus lambda I into x equal to 0. Solve this homogeneous equation. A minus 3i into x equal to 0. What is A? Here remember that A is nothing but, here A is nothing but A into A transpose. Since we are finding the eigenvector of A into A transpose, you have to replace A by A into A transpose, right? So write it A into A transpose minus 3i. What is A into A transpose? See, 2 1 1 2. 2 1 1 2 minus 3 0 0 3. This is A into A transpose minus 3i matrix. So this is equal to minus 1 1 1 and minus 1. So in this R2 gives you R2 plus R1. If you apply, what will you get? Minus 1 1 1 0 0. So you have rank of A into A transpose minus 3i is 1. So R is equal to 1, N is equal to 2, order of matrix, N minus R arbitrary constants, 2 minus 1, that is 1. So let us assume that Y is equal to K. Let us assume that Y is equal to K. So if you substitute in first equation minus x plus y is equal to 0 from here, what will you get? Minus x plus k equal to 0, x is equal to k. So for eigenvector corresponding to lambda is equal to 3 is, let us say this is x1, k and minus k and k, right? K and k. K if you take common 1 comma 1. This is x1. This is x1. Calculate the normal orthonormal vector, that is E1 is equal to x1 by norm x1. You will get 1 by root 2 times 1 and 1. So we got E1. Similarly calculate for lambda equal to 1. Case 2. Lambda equal to 1. You will get x2. What will be that x2? 1 minute I'll say. That x2 will be minus 1 and 1. That x2 will be minus 1 and 1. Normalized orthonormal vector of x2 is x2 by norm x2. So 1 by root 2 minus 1 and 1. After getting the eigenvectors corresponding to A into A transpose, we have to write model matrix orthonormal model matrix of A into A transpose we have to write. So let us say orthonormal model matrix of A into, that is U we have to write. So U is equal to, what is model matrix? Columns should be orthonormal eigenvectors, that is E1 and E2. Remember that eigenvectors in U should be written in decreasing order of their eigenvalues. Decreasing order of their eigenvalues. That is E1 का आइगन वैल्यू ज़्यादा होनी चाहिए E2 से. मतलब इसका आइगन वैल्यू 3 है, इस केस में इसका आइगन वैल्यू 1 है. आप E2 कामा E1 नहीं लिख सकते हो U को. दिस इज नॉट पॉसिबल. Remember that eigenvectors corresponding to largest eigenvalue should be written in the first column, then followed by next largest vector corresponding to next largest eigenvalue. So we have to write like this. What is E1 here? E1 is 1. So I'm writing the model matrix. I'm taking 1 by root 2 common. You will get 1 1 minus 1 1. You will get 1 1 minus 1 1. So we calculated U. In the similar way, you can calculate V also. So V you will be getting, I'm directly writing U, V. So this is, just I'm copying this, I'm writing here. Check it out. Sorry for the disturbance in between. 1 minute.